Good morning, everyone. My name is Tristan Haddad in the School of Architecture, and I'm here with two of our students working with us on the project who are going to introduce themselves.
My name is Zoe. I'm a second-year civil engineering undergrad student.
My name is Chloe, and I'm a fifth-year undergraduate architecture student.
So our project, the ReWind project, which is the reuse of decommissioned wind turbine blades, it's an NSF-funded project. And we're going to talk about the project in kind of four parts. We're going to talk about the problem, right? Why are we doing this? Why is it interesting? We're going to talk about the team, because the team itself is quite interesting and incredibly diverse. We're going to talk about our solutions, our proposed solutions, and then the technologies that we're developing that will allow us to actualize those solutions. So everyone has seen these massive wind turbine blades, and we love them because they produce clean, inexpensive energy. Now imagine, close your eyes and kind of imagine this. Imagine those blades, which are sort of on the order, the average blade is on the order of 50 meters. Imagine 10,000 of those blades every year coming offline and being stuck in a landfill. And that doesn't just happen one year, that happens every year. So the scale of this problem is enormous. These blades are designed with a roughly 20-year service life. They're coming out of service sometimes earlier than that for both technical reasons, but also for economic reasons, when power plants are repowering so that they can get more power out of their power plants. And we don't know what to do with them. This is a looming problem that's coming up, and we really are trying to get out ahead of it. It's estimated that by 2050, there will be 40 million tons of FRP, so fiber reinforced polymer, that's what these blades are made out of, 40 million tons annually coming out of service and going into either the waste stream, or hopefully what we're after is that it would be upcycled in a kind of circular economy and go into a second life application. So that's really what we're looking at. That's our problem. The team is really an interesting team. This is a tripartite, again, NSF-funded project. It's Georgia Tech here. It was previously it was Georgia Tech in Cooney City University in New York. Our faculty member, Larry Bank, who is not here today, and Russel Gentry, who is a Georgia Tech faculty member. Larry has come onto the faculty here in Georgia Tech as a research faculty, so it's all housed here in Georgia Tech. But then we're also partnered with two universities in Europe. We're partnered with UC University College Cork in the Republic of Ireland and Queen's University Belfast in Northern Ireland. Ireland has a lot of wind and a lot of wind energy, so this is really a problem that they're very interested in. The other part of our team that's been quite interesting is that it's incredibly diverse. We're not looking at this just from a technical perspective. We're looking at it holistically. So we're looking at the kind of technical issues, the environmental issues. We're also looking at the social and cultural issues. So we have a sociologist in Cork working on this problem. What are the sort of societal impacts? We have economics and business faculty looking at this in terms of what's the business case. We have geographers who are sort of mapping the whole problem out in terms of where's the resource and where could it be used in second life applications. We're thinking of this like the new forest, right? This is our future resource that can be harvested. And then, of course, we have architecture and engineering faculty here at Georgia Tech. So that's the team. Then talking about some of our solutions, we've run a couple of design studios and different courses here at Georgia Tech, working with the students to come up with different solutions, really a kind of design atlas, if you will, looking at different scales and different applications. We've kind of structured it as a small, medium, large situation in terms of different applications. And we have come up with a few that we think have real merit, a few applications, a few solutions that we think have real merit. And we're actually in the patent process now, working with some of the large OEMs. I won't name names, but some large OEMs that are very interested in looking at what we can do with these blades in second life applications. So these objects, again, these are they're very advanced, sophisticated components, right? FRP, it's an advanced composite material, but the geometry itself is also very sophisticated. It's a 50-meter, 150-foot long, single, rigid, stiff element, right? So what can we do with that? It has tremendous value. So we've looked at different applications. We've looked at using these as the vertical structure in high-power transmission lines. We've looked at using these in pedestrian bridges that could become part of a network or a kind of greenway of bridges across Ireland. We've looked at housing. We've looked at seawalls and sort of erosion controls. We've looked at lots of different things. And I'm going to let Zoe and Chloe talk a little bit about our team, our local team here at Georgia Tech, and then talk about some of our applications.
Yeah, so our team at Georgia Tech, it's a team of architects and civil engineers. One of the big ideas that we're exploring right now is the pedestrian bridge concept. So we're really looking at how we can use these blades as the main structural elements of pedestrian bridges. So we're looking at using the blades as girders, using them as a deck, or even using them in a cable-stayed bridge as the vertical tower. So there are a lot of exciting configurations that we're looking at, and we're really in the process of narrowing it down and possibly even prototyping it in the future.
So the other big project that we're working on here is for the power line transmission. So right now, the power line infrastructure is aging, and these blades, as Tristan mentioned, are made from this composite material that serves as an insulator, but also has strong structural properties. So these blades can be configured to replace the power lines. So right now we're going through different iterations of how those can be either designed in large groups, again looking at scale, but how they can be how we can use different figurations and configurations of the blades to replace power line transmission.
Yeah, and so, you know, one of the things that I maybe sort of skipped over, on the one hand, we're trying to keep this material out of the waste stream, and there's also a huge economic cost to these companies because there are big tipping fees, especially in Europe, that people are trying to avoid. On the other hand, we really are trying to build a business case that makes this a sustainable solution, because again, in 2050, we're going to have annually 40 million tons. So if you think about an element like a vertical a tower and an electric transmission line, that's a very expensive element, right? If you could replace, and that's, you know, virgin material oftentimes. So if you can replace virgin material with a reuse material, and you can take a $300,000 tower and replace it with a free element, there's a real case there, right? So I guess then lastly, what we're developing here are a series of technologies that will allow us to be able to capture and represent the geometry of these blades, because oftentimes the OEMs won't give us the drawings for legal reasons, right? They don't want liability. So we have to be able to kind of reverse engineer or data mine the blade geometry. We have to be able to represent the layups and the structural capacity and then analyze that through structural analysis, FEA, and all of that sort of stuff. And then the other thing that we're looking at right now is we're looking at kind of morphology mining. So can we scan these blades with LiDAR, photogrammetry, and then feed it into a genetic algorithm so that we can do a kind of best fit scenario to try to identify these blades and actually, you know, kind of in an automated fashion recreate the blade geometry, because we'll have to be able to represent and describe the blades in order to go through code reviews and actually use them in the built environment. So with that, ladies, do you want to add anything else? Okay, the project is called ReWind, so if you just Google RE-wind, it'll be the first one that comes up, so we'd love to hear from you. Thanks.